Hello, my name is Marcus with MLC CAD Systems in Stillwater, Oklahoma, and I'd like to take you through the process of establishing accuracy in a computer simulation, specifically SOLIDWORKS flow simulation. Now, when you're running a simulation software, it's a pretty basic process, right? You want to define the problem. What are you trying to figure out? You want to build a representative model, and using SOLIDWORKS, it's very easy to put something together, and then you'll set up an analysis and run it. And that study will kind of capture all the things that you know, and then you'll find out what the answer is. Now, the focus of this video, though, is the Converge, Calibrate, and Validate steps. Now, these steps are very important to make sure that the results you get are actually going to be relevant and accurate to the real-world application. And depending on how complicated your setup is and how complicated your application is, you should expect several iterations, and you'll generally learn a lesson each time you run one. So let's start with defining the problem. I like cold beer, and that's not a problem. I live in Oklahoma, and whenever you want something like a High Point beer in Oklahoma, they have to be sold at room temperature. So if you're not thinking ahead and you want to drink cold beer but you didn't buy it ahead of time, you're going to have to wait. Now, I have a freezer, and I tend to kind of put things in the freezer for a short amount of time to try to speed up the process, but I don't ever really know how long I should leave it in before it's ready to drink. And I definitely don't want to leave it in there too long, or else it's going to freeze. So all I need to do is take this generalized equation and solve for time. Seems pretty simple, right? Now, I'm going to take this setup, and I just built a refrigerator model, real simple, and put in some bottles and cans that I got off of 3D Content Central. I measured the freezer temperature and the initial temperature of my beer, and the actual setup of the study I'm covering in another video, but the results were pretty cool. So you can kind of see the bottles and the cans cooling off over time, and you'll see they kind of get cold from the bottom up. When I actually did the measurements of the results, I found that the bottom was generally a few degrees colder than the top was. Another view of that from a cut plot, and you can kind of see the distribution inside, cans on the bottom, bottles on the top, along with some probes of the temperature. And if I take that and I plot it across time, I can kind of say, okay, well, let's see here. The optimum temperature for the beer I'm wanting to drink is right around 35 degrees. The time to get to that temperature is about 30 minutes, so all I need to do is throw the beer in the freezer 30 minutes, and I'm ready to go. Awesome. But the question is it accurate? Is that right? Those were the default settings out of the box, threw it together, ran it, got an answer, and now the hard part comes. I have to figure out whether it's accurate. So I'm going to take you through three major steps that everybody should follow when you're using computer software like this to be able to make sure it's accurate. First thing we're going to do is converge it, then we're going to calibrate it, and then we're going to validate it. So convergence, it's important to understand that in engineering, everything should converge to an answer. You should define the problem statement in such a way that there is one generally correct answer for the problem statement. Convergence criteria are generally pretty standard across all software. The mesh is the most common thing you need to converge, and we're going to talk about that in this specific situation, but there are singularities that can be caused by geometry, by impossible situations. If you tell the software to do something impossible, it'll generally take a value such as stress, displacement, or temperature, and it's going to run it to an extreme or ridiculous value. For calculation parameters, I'm really referring to some of the steps and functionality that's built into the software to make a solve more efficient and go faster. If you go too fast, you might actually simplify the solution mathematically to the point where you miss the entire point of the problem. To simplify things down and really focus in on the new problem statement, because I'm starting my second loop here, the new problem statement is, what kind of a mesh density do I need in order to get an accurate solution? And as you see on the left, we have the setup is just going to be air kind of blowing over this thing, and I start out with basically 6 very big elements and then refine it and refine it and refine it. As the mesh count gets higher, the accuracy will generally get higher, but the solve time goes up. And that is the quandary. That is what we have to balance, is the accuracy with the performance and the solve time. So what I did is I set up a parametric study. Again, I'm going to put this in another video so that you can sit down and look at exactly how to build this. But I said as the mesh count increases, I would expect it to sort of narrow down and come to a final converged solution. And this did. It came into 61 degrees at 30 minutes, which, if you remember, 35 degrees at 30 minutes was my original prediction. So it's definitely not where I thought it was going to be. But this is good. I'm getting to a good solid answer. And you'll expect to see this converge as the mesh increases in density. And this is true of FEA, CFD, anything that you do, you're going to start to see that convergence. Now, here's the thing. You want to kind of know where you are so you can operate correctly. If you're too coarse, your results are going to be very inaccurate. They're going to swing wildly. From 35 to 61 degrees, that's a pretty big swing. I was firmly in the inaccurate zone when I first ran my original study. As you get over to the good area, and I say it's good because at this point you're not really using too many resources, but you are getting a very accurate answer. It's kind of the sweet spot, right? As you get further along, and depending on how complicated your study is, it's going to start to slow down without really any gain in accuracy. So you want to avoid that area unless A, the performance is not really a concern, or B, maybe you really are done and all you're trying to do is get one good final answer. So if that's the case, go ahead and crank it up one more time. There's a couple ways that you can kind of check for convergence. So it doesn't have to be by running this parametric study and graphing the relationship between mesh density and accuracy, or the result. You can do a visual inspection. On the left is some of my first studies that I ran, and you can see not only is it very few data points, but the geometry is so idealized that it doesn't even look right. It doesn't even look real. It's like it's a square bottle. Definitely that's not going to give us accurate results, and it doesn't. But as we get further along and more refined, you'll see that it becomes very much recognizable as a bottle. The accuracy, or the result is clearly visible, and this is the kind of mesh that you would expect to see if you're going to get accurate answers. So when you go to do this, this is how you do it. It's very simple, straightforward. Just run a study and get your result. But then refine the mesh and run it again and compare the two results. So if your result changes when you refine the mesh, that means it's mesh dependent, meaning the mesh that you chose, the settings that you chose, which have nothing to do with beer, they have something to do with computer modeling. If those affect the outcome, then you've got trouble. What you want is a situation where no matter what you do to the mesh, the result stays the same. We call that mesh independence. And you want to run it, refine it, and run it, and then compare. And continue doing that step until you see it flatten out. The result should be nice and steady from that point forward. Any more complexity you add, that's not going to change the result, because at that point you have the correct result throughout. So at this right here, I could actually jump back to run number 2 with the understanding that I was already converged at that point, and I could do most of my iterations there. Because I'm going to have a lot more work to do, I don't want to necessarily take it all the way out here into that slow region to continue doing my work. We're still fairly early in the process. Now, a few more notes on the convergence. Computer simulations take these complex problems and they break them down into data points, complex sets of equations, and convergence is happening in the background. It's the step that makes sure the answer is correct. What you're doing is a convergence that sits above that step, which is to make sure that the mesh and the settings that you specified and how you tell the software to run the study is making sure that those are correct. There are some methods that exist to kind of help you with this. There's adaptive meshing techniques, especially in simulation. There's an H-adaptive and P-adaptive that automatically corrects for error based on the mesh size. You can also do mesh quality plots, energy norm error. This is a curvature criteria plot, and there's also some brick quality plots that you can do in flow simulation that are really going to help you out with a very quick check to say, yeah, that looks good, or no, I'm concerned in this area about accuracy. So we've converged our solution. We now have a solution that, and a mesh size that we know is going to give us a good, accurate solution for this type of application. It's time to calibrate. Now, all the assumptions that we've made, how we set up the study, what materials we picked, the boundary conditions, all those assumptions, we assume they're valid, we assume they're good, but how do we know? And this is the step where we kind of break everything out into what we know and what we don't know. So what we know is the temperature of the beer, the volume of the beer, the geometry of the bottles, the software that we're using. You know, we know all these things, and we don't know how long to leave it in the freezer. But that's not all we don't know. There's a lot of unknown unknowns, and those are the ones that are going to get you. Now, you don't know exactly what they are. They might just be that the thing you thought you knew you didn't know, or it might be something you didn't expect. Maybe something that until you actually run it, or until you've seen it, you never would have thought about it. And so what we need to do is predict and control for the unknown unknowns. Now, we can't control for all of them, but we can definitely work on it and kind of calibrate it as much as we can. I love this quote. Remember that all models are wrong. The practical question is, how wrong do they have to be to not be useful? So we know this is going to be a wrong answer. The question is, can we make it a useful answer? And once we make it a useful answer, we now have something to work with. So we're going to calibrate it against actual results. If we can, we'll physically test the problem. Now, you can't always physically test the problem. Sometimes you can test a simplified version. So if you're building rockets, you may not be able to fully test the rocket engine by sending something up in space, but you can at least anchor it to the ground and run it on its side. That's a simplified test, but definitely gives you tremendous value and information regarding the full system. You can compare it with existing test data. You can also compare with things like known failure rates, benchmarks of publicly available data. I've even gone on YouTube and watched people stick a thermometer in something and run it just to see what would happen, and I was able to kind of compare my results against that. I did that with a grilled cheese sandwich, in fact. That's another video for another day. So for my first test, I just said, well, let's just go throw a beer in the fridge or in the freezer for 30 minutes. So my first prediction was 35 degrees at 30 minutes, but we found that that was not even close. We converged the study at 61 degrees, but then when I did it and measured it, we got 48 to 50 degrees. I did it twice, one on the top shelf, one on the bottom shelf, and you can kind of see there was a couple of degrees of difference. So I'm still not there, but I'm not sure why. But something occurred to me. What about the airflow? Depending on where I put the bottle, it might be surrounded by boxed frozen dinners, or it might be on an empty open shelf. And in the example that I created earlier, everything was nice and wide open, and then in this smaller study, I had it in this nice tight box. So this is where I thought, okay, you know what I'm going to do? I'm going to run a whole range of airflow velocities. And as the velocity increases, I would expect the convection to increase, and I would expect it to get colder faster. The question is not so much what velocity am I going to need to get, because that is kind of the answer I'm going to go for. The question is which velocity best represents my refrigerator or my freezer and my specific application, since that's what this is all about, drinking my beer. So after 2 hours in the freezer, starting at still air and working all the way towards a direct fan blowing directly on it, you can see at the direct fan, we nearly completely normalize the temperature to the freezer, 0 degrees. And as the air velocity increased, we see quite a bit of movement. So it's very sensitive to that variable. The air velocity is going to make a huge impact on the time it takes to cool down, and therefore the time we need to leave it in the freezer. So here's a real quick video animation, just kind of a portion of each bottle. On the right is the direct air, on the far left is the still air, and you can see how quickly they start to diverge, even though they're in the same study and the same setup, with just slightly different velocities of air. So here is the plot versus time of the temperature for each one of those examples. Up along the top is still air, down along the bottom is that blowing air, and my test data said at 50 degrees at 30 minutes. And if you look at that, you end up with this orange line. That orange line is the 25 inch per second velocity. So that's what my freezer has, is a very light breeze. If I take that data and I now extrapolate it, and I turn it backwards and sort of, instead of finding the velocity that I need, I use the velocity to predict the time it takes, you'll see that at 50 minutes, you get your TTODT, which is the time to optimum drinking temperature at my house. So 50 minutes, that's our answer, right? That calibration steps helps us to test the assumptions, the setup of the study, the input values, knowns, unknowns, all the various different things we have that we can't necessarily control for, or we don't have the time to exhaustively research. We can now kind of get a good answer and say, yes, I believe this model matches what we're actually doing in the real world. Now, the more data you can have, the better, and you may have to do this multiple times, but each time you do it, you're likely to learn something new. Which takes us to the last step, which is the validation step. Now, we need to make sure that these are right, especially if we're going to be building 1 million units. It's also possible that it's required. Some applications, some ratings agencies or quality standards require that you have a physical test, and they lay out the methodology very specifically. The validation step should be basically the final calibration step, but no further adjustments should be required. Now, if you're going to do a physical test, you might think, well, why in the world would I run a computer model if I'm going to run a physical test? And the answer is because physical tests are expensive. You have to build the prototype. You have to put it in the lab. You have to run it. You have to measure it. And if you have to do it over again, you're wasting a tremendous amount of time. Plus, by understanding where you expect to see failure, you can actually observe the test even better and predict and create better solutions so that you don't have any failures in that physical testing. So now it's time to validate or drink beer. And I just wanted to point out that I'm doing this for work, so that technically makes me a professional beer drinker. So let's go see what happens once we actually throw the beer in the freezer. And now, let's see what's going to happen in 50 minutes. Okay, it's been 50 minutes. Let's take a look, see what we got. We predicted 35 degrees at 50 minutes. The average temperature of all the different tests we ran was 35 degrees at 50 minutes. It was perfect. Now, the thing is, it wasn't exactly perfect because there was a few things happened. On the first beer, I got a little bit excited and I checked for the status at half an hour, and it was 47 degrees, which is right about where I expected it to be. But then it almost didn't cool at all after that. That warm air could not get pushed out by the cold freezer in that last 15 minutes or 20 minutes. So I really kind of messed up that study run. The second one was 32 degrees. That's awesome. Then came 38 degrees, and I realized I had been opening and closing the door and doing videos with the doors open, that the freezer was cycling and it wasn't quite keeping up with the demand of me constantly making videos in the freezer. So the last one I did two at once, the top shelf and the bottom shelf. And on the bottom shelf, I actually laid it on its side. Somebody told me it would go cool faster on its side, and it did. So we're seeing some variation, but really when you're talking about a non-precision piece of equipment like my beer fridge at my house, it's to be expected. So what have we learned? We've learned quite a few things about beer and freezers, but the main thing is the three-step process that you always want to follow whenever you're running a computer simulation. Converge the solution. You need to make sure that the mathematical setup, the mesh, the settings of the solver are going to give you good optimum results, and there's a pretty easy step to reach that convergence. The next step is going to be calibration. With calibration, you're taking the results that are coming from your computer and you're relating them to real-world results. And the last step, of course, is the validation. Now, this might just be simply sending the product out the door, or it might be that physical test to make sure that everything worked out the way you want it to. But by the time you get to that step, you should understand quite a bit about your solution and about how to accurately analyze that system.